I hope
afternoon, ma'am.
you're doing good.
Good afternoon, ma'am.
Ma'am.
Good afternoon, ma'am.
Good afternoon,
Good
ma'am.
afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon. So I hope all of you are doing fine.
Yes, ma'am.
Yes, ma'am.
Right. So we will be continuing with lesson 1 today. Okay. This is our theory lecture. So we will be continuing with Boolean algebra in lesson number 1. Okay. That is where we left last time. Okay. I'm going to be presenting my screen to you. Do let me know in case you can see my screen. Okay. Should we begin? I think there are, or we should wait another minute for the people to join in. 50 people already there. I think by the time I start sharing my screen, if somebody wants to come in, okay, then I will not allow anybody. Okay? Yes?
Yes, ma'am. Fine.
Yes, ma'am.
So we did last time, if you remember, we had talked about the logic gates. We had finished talking about the logic gates. Before that, we had discussed truth tables. So then we practiced how to, perform the logical operations. We practiced the, how to do basic ORing, ANDing using these truth tables. Okay, so there were two objectives behind this practice questions that I did with you. One was that you would learn the basic or and not, okay, these logical operations, and the other was obviously that in your theory paper you get questions which involve making truth tables. Okay. I also gave you an assignment. I hope all of you have submitted it. Those who have not
Yes,
submitted,
ma'am.
please
Yes,
submit.
ma'am.
Okay. So I am going to be giving you multiple assignments. For example, in today's lecture as well, I will give you some questions to work upon in Boolean algebra. Now, please see, students, unless and until you practice these questions with your hand, you will not get a hang of Boolean algebra. Okay, so there are certain things which need to be done by hand. That is why I'm putting in assignments for these things. Okay, now out of these assignments later, then I will pick up any two assignments and grade them. Okay, so I will randomly choose two assignments for grading purposes. So you need to be aware now, okay, you need to be very cautious right now as well, that you have to submit your assignments in time, okay, and you have to ensure that you do them correctly. Clear? Okay. Later, I will pick any two assignments and I will grade them. And that will be added to your internal assessment. Clear? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right. Right. Okay. So let's start today's lecture. Okay. So what is Boolean algebra? I told you this earlier, but let's go over it once again. See, Boolean algebra was introduced by a mathematician, Sir George Boole, in 1847. He introduced Boolean algebra, the concepts of Boolean algebra, in one of his books. And what did Boolean algebra exactly dealt with? See, the normal algebra deals with the numbers. Okay, so the basic operations, numerical operations are dealt with in the algebra, right? In Boolean algebra, however, we restrict ourselves to Boolean variables. Boolean variables means the binary variables, and the operations are limited generally to the logical operations. What are the logical operations? And, or, and not. So let me ask somebody to read the screen. Will somebody volunteer to read my screen?
Yes, ma'am.
Who is this?
Dipali.
Yeah, Dipali, thank you. Yeah, please read the screen.
Boolean algebra was introduced by George Boole in his first book, The Mathematical Analysis of Logic, 1847. Boolean algebra is the branch of algebra in which the values of the variables are the true and false, usually denoted 1 and 0 respectively. Instead of elementary algebra, where the values of the variables are numbers and the prime operations are addition and multiplication, the main operations of Boolean algebra are the conjunction and denoted as you all can see, the disjunction or the negation not. Next point,
Conjunction, which is conjunction. Then
and
conjunction means and operation, right? Then disjunction is another name for the or operation, and negation is the complement or not. Is this clear? Yeah,
yes,
continue.
ma'am. Yes. It is thus a formalism for describing logical operations in the same way that elementary algebra describes numerical operations.
Is this clear? Is this clear to
Yes, ma'am.
everybody now?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay,
Yes, ma'am.
okay, good. The next thing that we need to learn is the basic identities, that is the basic laws of Boolean algebra. Okay, so one by one, I'm going to introduce these laws to you. These have been taken from your book. Okay, the first law is the also known as the property of zero. It says x or zero gives us x. Now, what does this mean? X here is supposed to mean a Boolean variable. It is supposed to denote a Boolean variable. Now let us see if this is actually true. Okay. So suppose I have a Boolean variable x. Okay. Now what are the values that this x can take?
0 or 1.
Zero,
Zero
one.
and 1. Yes. So let's say the first case is that x is 0. So 0 or 0 would mean, would give me
Zero.
Zero.
0. The other value that x can take is,
1.
One.
and 1 or 0 would give me.
One.
One.
So whatever I put in the value as x, I get the same result. Yes?
Yes, ma'am.
That is why the first law, that is the property of 0, tells us that x or 0 is always gonna be x. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Good. Let us look at the another variant of this property. So this is again the second point, the second identity of Boolean algebra that you see here is again called the property of 0. The only variation that we're doing here is that we replaced the OR operation by the AND operation. Okay, so let us verify this as well. Now, as before, x can take only the values 0 and 1. right? This time I'm going to be ANDing this value with 0. So what will I get when I AND 0 with 0?
0.
0.
0. Very good. The second time I will try and AND the other value, that is 1 with 0. What will I get?
0.
0.
0
Zero.
again, right? So that is why the second variant of the property of 0 states that whenever any Boolean variable is ANDed with 0, it always gives me a
0.
Zero.
yes. Now, the next property is the property of 1. Okay, so property of 1 says that, can you work this out yourself? Let us see, what do you get? What would x or 1 be equal to according to you? Let's see.
1.
1.
You always sit with a pen and paper whenever you come for my class, right? Yeah. Can you just work it out and let me know what do you get?
Ma'am, 1.
1.
1, ma'am.
1 in both the cases.
In both the cases, it is going to be 1 because by definition, the OR gate is going to give me 1 even if there is a single one. So by the definition itself, we could actually see that since a, uh, at least one 1 was a given, therefore the answer had to be 1. Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Good. Let us look at the another variant of property of 1 now. X and 1 is equal to. Let us see what this evaluates into. Any idea what this would evaluate into before we
X.
actually do it?
X.
Yes. Why? Because by definition of the AND gate, the first time I'm going to evaluate AND the 0 with 1, I'm going to get 0. The other time I'm going to get 1. So whatever I'm putting in as X, I'll get the same as the output. Is this clear?
Yes, ma'am.
Yes, ma'am.
Good. The next is the law of idempotency. Okay. So it says X or X is equal to, let's find out for ourselves. So the first case is going to be 0 or
0.
0. Yes. It will give me a,
0.
0.
and the next case is going to be,
0, 1,
1 or 1.
1.
which will give me a,
1.
1.
can I say X or X is equal to X then?
Yes, ma'am.
Yes,
Yes, ma'am.
Yes, but I did a little mistake here. Please note this. If you are using small letters to denote Boolean variables, then at all places you must continue to do the same. So if I'm using a capital letter here, then I must use a capital letter here. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Right. Next is another variant of the same law, that is the law of idempotency. Let us see this variant with AND now. So any idea what it would give us? I've done it on screen for you.
Yes,
Same
ma'am.
X
It is the
value.
same.
It is obviously going to be the same. So obviously if I'm going to AND 0 with 0, it's going to return 0 to me. And if I'm going to add a 1 with a 1, it is also going to return a 1 for me. Yes or no?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Good. Okay. So let's see the next law then. So X or X is equal to X. X and X is also equal to X. By the way, you need to learn all these identities. So the first assignment today would be that you're going to actually write down these identities on a piece of paper and learn them. Okay, if you want to do Boolean algebra, if you want to solve Boolean expressions on your own, then learning these properties is a must. Okay, now the next thing that we're going to see is we are going to AND x with its complement. Okay, let's see what we get. So if I had put in a 0 and I AND it with 1, what will I get?
0.
0.
0.
Yes, right. And if x was a 1, obviously I'm going to AND it with its
0.
complement, which happens to be 0. And again I'll get what?
0.
0.
0, right? So this is always gonna be 0.
0.
What if I replace this AND by OR?
It would be 1 on both the cases.
Yes? Come on.
One in
Ma'am, it
both
is 1 in both the cases.
I will guarantee a 1, at least, 1 in both the cases, it would always result in a high output.
1.
Yes or no?
Yes, ma'am.
So you see x or x dash is always going to be 1 and x and x dash is always gonna return us a 0. Is that clear?
Yes,
Yes,
ma'am.
Yes, ma'am.
Up till now, is there any problem?
No, ma'am.
No, ma'am.
Okay, let us proceed to the next law. This is the law of commutativity. So this is just the same as you've done with addition and multiplication earlier in normal algebra with the normal numbers. So it simply states that if x and y are two variables, then x or y would always be equal to y or x. Okay, again, we can verify this. So let these be the two variables x and y. Okay, x and y, and suppose their initial values are 0 and 0. So what will I get? 0.
0.
Yes.
Yes, ma'am.
The next set of values that they are going to take is 0 and 1. What will I get?
1.
1.
Very good. The next set of values that they are going to take is
1 plus 1 is 1.
1 plus 1.
which will all
1.
also give us 1, and a final set which is 1 or 1, which is also going to give us 1. Yes, let us now see this. Let us now reverse the positions of y and x and see what do we get. So of course, what have I done? I've simply reversed their positions. But so let me put 1 here. The first case is 0 or 0. Yes. The next case is when y is 1 and x is 0, right? Yes. The third case is when y is 0 and x is 1. And the final case is when both of them are 1. Do I get the same output this time as
Yes,
well?
ma'am.
Yes, ma'am.
Yes, ma'am.
Yes or no? Yes or no?
Yes, ma'am.
So that is why commutativity holds over the or operation. Okay, we say that commutativity holds over the or operation. Same is the case with the and operation. Okay, same is the case with the and operation. So I leave it as an exercise for you to verify the commutativity over and. Is this clear? So in the same way, please verify. Next, we move over to associativity. So you remember we used to say A plus B plus C grouped in any manner would give us the same result.
Yes, ma'am.
Yes or no,
Yes, ma'am.
student?
Yes, ma'am.
Yes.
Yes.
Right. So the same is true for both the or operation and the and operation. Okay, so again, how can you prove this? The simplest way to prove this would be construct a truth table for the left hand side and for the right hand side, and you could match their outputs. For the same set of inputs, we match their outputs. If the outputs are same, then we say that the two expressions are, the two Boolean expressions are equivalent. Is this clear? The way we've just
Yes, ma'am.
proved the commutativity of the OR operation. Is that okay?
Yes, ma'am.
Yes,
Yes,
ma'am.
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 So this is again something that you are going to do on your own. Okay, because these are actually commutativity, associativity, and the next is distributivity. These are things that you've already done with all the numbers. Now what we are actually just doing is that we are just restricting the domain of those variables from all the numbers to the Boolean, that is to the binary, and we have changed the nature of the operations now. Okay, so plus does not mean a normal addition now, it means a or, and a dot means, instead of meaning the multiplication, it now means a
And
logical and operation. Is this clear?
yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so distributivity is again something that you have been doing quite a lot. Yes or no? When we open
Yes,
the
ma'am.
Yes,
what do we
ma'am.
get? XY or XZ. Okay, so again, this is left to you as an exercise to verify this using the truth table. Okay, so you'll get ample practice of the truth tables as well. I move on to point number 14, okay, where you see another variant of the law of distributivity, right? Now, this is what I want you to remember. This is also an identity which you will be using a lot while solving the Boolean algebraic expressions. Is this clear? So this is another form. This is another form of uh, distributivity, and I think I have an exercise listed for you somewhere which proves this using the Boolean algebraic identities. Okay, and obviously you can also do it using the truth table method as we just saw. Okay, so I'll leave the proof of this for the moment. I'll first take up the uh, resolution of
Ma'am, excuse me.
small. Yes, sorry.
Ma'am, in this identity, it should be x plus y dot z instead of x plus y dot x.
Yes, yes, you are right. Yes, you're very right. This is a, although this is a picture that has been taken from the book as it is, okay, but yes, you're right. This should be X or Y, Z. Thank you. Who is this? What's your name, beta?
Nandini Vashisht.
Nandini Vashisht. Thank you very much. So I'll just make the correction here. Okay. I'll just make the correction here. Though this picture has been taken from Morris Manor only, but maybe, you know, sometimes So this is x or yz. Or let me just write it down for you. X or yz is equal to x or y.
Ma'am, the right hand side is fine.
X or z. Yeah. I'm just writing the entire thing so that people don't get confused. Okay. So this is it. Okay, students, have you got it? What was the problem? Did you get? Nandini, have
Yes, ma'am.
you checked this there? Yes, it was a typo in the book itself.
Yes,
That means,
ma'am.
okay, it was a typo in the book itself. This has to be x or yz is equal to, so x or y, you can see this, x or y is equal to x or y, okay, ANDed with x or z. So I told you that we will be taking proof of this Boolean identity somewhere later, okay, somewhere later. And because first of all, I want to take simple proofs for you. Okay, then I'll graduate onto the proof of this identity later. But using the truth table, again, you should satisfy yourself that this is true. Okay. Now, the next two identities that you see in point number 15 and 16 are very important again. They are called De Morgan's law. They are called De Morgan's law. So what are we doing here? We are in the first case that you see here, taking a complement of an OR operation between the two Boolean variables. So x and y are being ORed and we are taking their complement. Okay. So what is the output that we get? The output that we get is replacing each Boolean variable by its complement. Okay. So x gets replaced by x complement and y gets replaced by,
Y
I complement.
complement.
yes, and or gets replaced by and.
And
Okay, and or gets replaced by and. Okay, when nothing is written, it implies,
And
I told you, right? And. Okay, is this clear?
yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So whenever De Morgan's law is applied, each variable is changed to its complement form. And if in the initial expression we had an OR sign, it would be replaced by a AND sign. If the original expression, however, had a AND sign, it would be replaced by a OR sign. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
This is because and OR are said to be duals of each other. Okay, and that is why this law is also sometimes known as the law of duality. It is also known as the law of duality.
Duality.
So in other words, if you are asked to find the complement or dual of a particular algebraic expression, okay, what are these? These are all algebraic expressions, yes. So if you are asked to find a dual or complement of a Boolean expression, then what you have to do is you have to simply apply the De Morgan's law. Okay?
Yes, ma'am.
Are you there, students? Are you able to
yes,
understand?
ma'am.
Yes,
Yes,
Are
ma'am.
you
ma'am.
able to?
Yes, ma'am.
Okay. So in the identity number 16, you see just the opposite of this identity, okay, where the OR operation has been replaced by the AND operation. Here, again, you see when I try and take the complement of x and y, what will I get? I will get x and y in their complemented forms. Yes?
Yes, ma'am.
And the AND operation replaced by a
Or operation.
Operation.
OR
Yes,
operation.
ma'am.
Or operator.
Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Right. So you will see this will become, all these laws will become more concrete for you. They'll become more clearer for you once we solve certain Boolean algebraic expressions with them. Okay. Next is the law of involution. The next thing that you see on your screen is the law of involution. Involution means when we involute a variable or complement a variable. Okay, so obviously you've seen that when I complement a particular variable x, we write it as x complement. But what we are trying to do here now is we are trying to take complement of complement. This is known as involution. Okay, so what is x complement ka complement? It is x itself. Now this is very easy to verify and we can do right here. We can do it right here. Okay. So as before, let's take a Boolean variable x. So if x is 0, then what would be x dash?
One.
One.
It would be
One.
1. And what would be the complement of this x dash now? Again,
Zero.
Zero.
yes or no? Is this clear?
Yes,
Yes, ma'am.
ma'am.
Yes, Yes, ma'am.
Let us look at the other case when x is equal to 1. So its x dash is 0.
Zero.
And when I take the complement once again, it again returns to its
One.
normal value, which is 1. Yes. So that is why we say x dash ka dash, that is the complement of x complement is x itself. Is this clear?
Yes, ma'am.
Yes.
Ma'am.
Good. So these are the basic identities of Boolean algebra. Okay. Now let us go on to do some practice solving some Boolean expressions with the help of these identities. Now, what do I mean when I say solving some Boolean expressions? Solving Boolean expressions means actually simplifying them to obtain a more optimal form. Now, why to do this? I'll come over this a bit later when we start with Carnot maps. See, if this is the expression, for example, you can see here. Can you see this expression here?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
This is a big expression, yes or no?
Yes, ma'am.
Yes, ma'am.
If I were to implement this directly, I would have to use so many OR gates. How many? 1, 2, 3, 4 OR gates. How many AND gates? 1, 2, actually more than that, because this is again, okay, chalo. Let's just count on the face of it. 1, 2, 3, and then, we also need a NOT gate here, right? So, and moreover, this is such a complicated expression, okay? But when I solve it, okay, when I solve it means simplify it using Boolean algebra, or you learn Carnot maps, which will come a bit later. So using any of these methods, when we simplify these expressions, you can see what is the simplified expression that we're getting here. It is only a plus c. This is to say that this is same as this. So can you imagine building a logic circuit for this and building a logic circuit for this? This is obviously gonna be much more simplified. Yes or no?
Yes, ma'am.
Yes, ma'am.
And it is also gonna require so many less gates. Economical, easier to construct such a circuit, easier to maintain, easier to debug. That means if there is a problem somewhere in the logic circuit diagram, logic circuit later, then it is easy to construct. Yes or no?
Yes, ma'am.
Yes, ma'am.
So that is the rationale behind trying to simplify the Boolean expressions. Okay?
Yes, ma'am.
Right. So let's move on to solving certain Boolean expressions ourselves. So let me take a couple of problems from your textbook first. Okay. So the first question is, determine by means of a truth table the validity of De Morgan's theorem for three variables A, B, C. So you've seen the De Morgan's theorem for two variables. The same theorem can be extended to multiple variables n, where n can be any number. Okay. So what you see here are three Boolean variables A, B, and C. When I try to take the complement of their AND, what will I get? I will simply complement each of these variables, A dash, B dash, C dash, and replace all ANDs by corresponding
Or.
ORs. Is this okay?
Yes, ma'am.
So the first thing is trying to find out what the dual or complement of a function is using the De Morgan's theorem. Now, what this question is asking us to do is that establish that the De Morgan's theorem works for three variables. So what do we have to do? We just have to construct a truth table in which one of the output columns is going to be this and the another output columns is going to be this. And then we are going to compare those, that for the same input combinations, if we have the same outputs in both these columns, then obviously we can say that the truth of this identity is established. Yes or no?
Yes, ma'am.
Okay. So you can see, can you do it on your own first before
Yes, ma'am.
I show you the screen?
Yes, ma'am.
And then we can compare? Yes or
Yes,
no?
ma'am.
Yeah, okay, good. Please do it and show it to me. Okay. Show me your notebooks. Once you do it, please let me know. And
Can,
side
ma'am.
by side, just getting your attendance link. Okay. The Google Drive was very slow today morning. wasn't really working, so I postponed it. So nobody was able to do it up to now. Has nobody been able to do it?
Done, ma'am.
Ma'am,
Done, ma'am. Ma'am, done.
Okay,
Done.
show me your responses. Or you can just show me your paper. You can turn on your videos and show me your papers.
Is it not visible?
No, let me just see. No, it is.
I have
Yeah,
on the video.
now it is. Yeah, now it is. Yeah, Yashi. Okay. Yeah, Yashi. So, Anu is also sharing a screen. Let's see her answer.
Ma'am, I have also shared Disha.
Ma'am,
Okay.
I also shared Nandini Vashist.
Just share
and
one by
Dipali.
one, okay? Just share one by one so that all of us are able to see. I can't see anything. I can't see anything. Anu, I cannot see your screen.
Ma'am, I think network issue.
That's okay. That's okay. You can just uh, turn on your video and show me your notebook. Yes, that's right. Okay. Come again. Come again. Let me see. Please come again. Let me see. It is wrong. Second, A or B or C. In the second case, 0 or 1 would be 1. Can you just progress the register a bit higher? I can just see the titles. No, this is not right. This is not right. Let us see somebody else's. Who else would like to show me?
Ma'am,
Ma'am,
Disha.
Nandini
Ma'am,
Vashist.
I'm sharing
Okay.
my screen.
Dipali. Who is this
Yes,
Dipali?
ma'am. Yes, ma'am.
Let's see Dipali's answer. But I can see your complete screen. A dash, B dash, C dash. Okay. Yeah, A dash. I think actually, you know, this is a lot of problem zooming in. Okay. Okay. Good try, everybody. Good try. Let me just show you how it is to be done. Yeah. Okay. So, please see. We are going to be first working out the left hand side. Okay, so these are the 8 input variations of the 3 binary variables that we always take. Okay, that is 0000001 that I told you to memorize. 0000001, 010, 011, 100, 101, 110 and 111. Okay, these are the 8 input combinations. Now, corresponding to that, first we will calculate A and B and C. Simple. Okay. So obviously, the only time it is going to be 1 is this case when all three binary variables are 1. In all other cases, it is going to be 0. Are you with me?
Yes, ma'am.
Have you understood this? Do you
Yes,
think
ma'am.
this is
Yes,
right?
ma'am.
Good. Good. Now, the next step is taking the complement of this. So obviously, I'll get a 1 in all these rows and a 0 in the final row. Clear up till now?
Yes, ma'am.
Yes, ma'am.
Yes,
Any
ma'am.
problem? So we have up to now, what we've done is we have worked the left hand side of this expression. Okay. Now we have to work this out. So for working this out, we must find first A dash, then B dash, then C dash, and then we will OR these three columns. So this is just obtaining a knot of these variables. So you can see that in the A column, we have first four rows as 0 and then the remaining four as 1s. So in its complement, we will have first four rows as 1 and the remaining four would have zeros, right? B dash, similarly for B dash and C dash, we will simply apply a NOT gate and we will get their complements and then we OR them, right? So we see that there is only a single case where there is no one. Yes, in all other rows, you will see that when we try to OR A dash, B dash, and C dash, there is at least one which is available, right? So the output of all these rows is going to be, come on, children, are you there? Yes or no?
1.
So the output of all these rows is going to be 1. And the only case where the output is going to be 0 is the last row where there is not even a single 1. Is this clear to you?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, good. So I will stop here today. Okay, I will stop here today. But I want you to please practice these expressions, building truth tables on a piece of paper. Please take a piece of paper and start doing these questions yourself. Okay, so you need to learn these identities and you need to start solving the Boolean expressions yourselves, building the truth tables yourself. Am I clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay, okay. So you are going to require a lot of practice there, okay? Because a couple of answers that I checked were not correct. So next class again, I am going to we will still, you know, we still have to solve a lot of Boolean algebraic problems. I want to take a lot of practice there. So I request you to be present with a notebook and a pen, and I'll ask students to show me their screens. Okay. So I'll ask you
Okay,
to
ma'am.
present on your screens, turn on your screens and show me. Okay?
Okay,
Okay,
Okay.
ma'am.
ma'am.
Okay, ma'am.
Okay,
Okay,
good,
ma'am.
good. So I'll just share the attendance with you. Please wait for a minute. Just a sec, beta. So I'm sending first the attendance for lab for B3, which I could not circulate earlier. Okay. Batch B3, please fill in your attendance for your lab. Okay. And next I'm going to share with you the attendance for the theory class.
Lab link for B3 only, na?
Yes. It was lab for B3 today, na?